You know how the Laplace transform can take a function and sort of encode it? It turns a signal we understand, something that happens over time, into this more complex message in the frequency world. Well, today, we're going to become the code breakers. We are going to crack that code and bring the original message right back where it belongs. Okay, let's get into it.
This formula you see right here, this is basically our entire mission. We get handed this f of s, this encoded message living in what we call the S domain, and our whole job is to apply this inverse Laplace transform to get back to f of t, the original meaningful function back in the time domain, which is where things actually make sense to us.
So here's the game plan for today. First, we'll get a handle on what our mission really is. Then I'm going to give you the key to everything, your codebook. After that, we'll start with some simple pattern matching, move on to breaking down tougher problems, and then I'll show you the master key for the trickiest codes out there. Let's do this.
Right, so think of this as a journey home. We've been working in this abstract world of S, which is all about complex frequencies. Now we're traveling back to the familiar, comfortable world of T for time. Because, that's where the real world is. It's where the physics happens, where the engineering matters.
Let's really lean into this code-breaking thing for a second. F of s is like a garbled, encrypted message. It doesn't mean much on its own. It's our job, as the detectives here, to use the right tools and techniques to uncover f of t, the crystal-clear original message that was hidden inside all along.
You can't be a code breaker without a codebook, right? Well, for us, that codebook is the Table of Inverse Laplace Transforms. And I'm not kidding, this is going to be your best friend. It has all the common patterns, all the known codes that we're going to be searching for.
And here it is, page 1, entry 1, the absolute bedrock. The inverse transform of 1 over s is just 1. That's it. It's the simplest pattern imaginable, and pretty much everything else we do is built on top of this idea.
Okay, now the codebook starts getting really useful. Look at all the heavy hitters we've got in here. We have patterns for different powers of t, for those crucial exponential functions, and of course for sine and cosine, the functions that describe basically anything that wiggles or oscillates. These are absolute bread and butter patterns.
And believe me, this codebook has your back for some seriously complex stuff too. It's got these shifted forms for when things get a little trickier, like when you're dealing with decaying waves. We're not going to get lost in the weeds with these today, but it's good to know they're in here, ready for when you need them.
All right, codebook's open. It's time to actually crack a code. Let's start with a couple of straightforward ones, where the encrypted message is a perfect match for something right out of our book.
Okay, here's our first target. F of s is equal to 1 over s to the 4th power. Now take a look at that. Does it ring any bells? Kind of looks like that power rule we just saw, doesn't it?
Let's put them side by side to be sure. Our problem has s to the 4th on the bottom. The codebook form has s to the n plus 1. So if n plus 1 equals 4, that's simple. Our n has to be 3. Okay, we're close. But wait a minute. Our numerator is a 1. The codebook says it needs to be n factorial, which in our case is 3 factorial. So we're not quite there yet.
And here's the trick. This is so clever. To make our problem look like the codebook pattern, we multiply by 3 factorial over 3 factorial. I mean, that's just 1, right? We haven't changed anything. But what we've done is we've snuck the 3 factorial we needed into the numerator. Now the part inside the transform is a perfect match for t cubed. The extra 1 over 3 factorial we have on the outside just tags along. And since 3 factorial is 6, boom, our decoded message is t cubed over 6.
Okay, that was great for a single, clean pattern. But what happens when the encoded message is a bit messier, like it seems to be a mix of a couple of different codes all jumbled together? Well, for that, we need a new tool.
This property, linearity, is an absolute game changer. All this math really says is that if you have to find the transform of a bunch of things added together, you can just deal with them one at a time. You can break one big, ugly problem apart into several smaller, friendlier ones. It's fantastic.
So check this out in action. At first glance, this fraction looks like a mess, right? It doesn't match any single thing in our codebook. But thanks to linearity, we can just split it right down the middle into 2 separate fractions. Suddenly, that first piece on the left looks an awful lot like the pattern for cosine. And the piece on the right, that's almost a dead ringer for the sine pattern. We just decode each piece on its own, stick them back together, and there's our answer. So powerful.
All right, we're getting good at this. We can handle simple patterns, and we can handle sums of simple patterns. But now we face the boss level. What do you do when you get a complex fraction that doesn't look like anything in our codebook?
And this is the moment. This is where you might feel that sense of panic rising, right? You're staring at this expression, you're frantically flipping through your code book, you've tried linearity, and nothing. No matches. So what do you do now? Don't panic. We have one more tool, and it is our secret weapon.
The strategy is called partial fraction decomposition. And here's the 3-step attack plan. First, we're going to take that one horrible fraction and break it into a sum of much simpler, happier fractions. Second, we'll have to do a bit of algebra to figure out the new numerators, the a, b, and c. And finally, the magic part. Each of those new, simple pieces will be a pattern we can easily find in our codebook.
Okay, this part here is the real roll-up-your-sleeves algebra, but watch how it works. We set up our big fraction to equal a over the first part, plus b over the second, plus c over the third. Now comes the heavy lifting. We have to solve for a, b, and c. And as you can see, the trick is to plug in clever values for s that make most of the terms just vanish, letting us solve for each letter one by one. And after all that work, look at this! This is the payoff. Our one impossible-looking transform has turned into 3 incredibly easy ones. Now all we have to do is find the inverse of these simple little terms. And guess what? Each one is a perfect match for that exponential pattern, e to the at, from our codebook. We did it! We cracked the toughest code.
Okay, we've just learned some seriously powerful math. But it's totally fair to take a step back and ask, why? What's the point of all this decoding? Why does it matter?
So let's just quickly recap our master strategy, our go-to playbook. Step 1, always check the codebook. See if you can get a direct, easy match. If not, step 2, see if you can use linearity to break the problem into smaller pieces you recognize. And if you're really stuck with a monster fraction, step 3 is to bring out the big gun, partial fractions. That's your secret weapon.
And this is why it all matters. This isn't just about abstract numbers on a page. The ability to take a real-world problem, encode it into the S domain where the math is easier, solve it, and then decode it back into the time domain where we can understand the answer, that is the key to modern engineering and physics. This is how we analyze electrical circuits, the vibrations in a bridge, complex control systems, you name it. You haven't just learned how to decode a function, you've learned the fundamental language used to describe the dynamic, moving world all around us.